We are currently at the same place in the day class that we are in the night class, and we don't have a day class tomorrow. So let's just go over some sort of review questions. Wait till next week to start working with free body diagrams and stuff. Okay, well, so let's just go through some 2D kinematic type problems. Okay, so let's say that we have an object that initially moves with a velocity vector of 30, negative 10 meters per second. So first, what's an acceleration vector that would speed the object up without any turning? And second, what's an acceleration vector that would slow it down without turning? And then third, let's say that the acceleration vector is negative 20, positive 5 meters per second squared. What's the object's displacement in 10 seconds? Okay, so let's start with A and B. Take a few minutes and see if you can think through that one. There's a question a lot like this on the 2D homework. And then I'll talk about A and B, and then I'll give you some time to work on C and see if you can think through that. Okay, so go ahead. Talk to each other. Talk to me if you get stuck. So for A, the acceleration has to be in the exact same direction as the velocity vector. And one way you can think about that is, remember that if you multiply a vector by a positive number, that doesn't change the direction. So you can think of this as the acceleration is equal to some constant c times that velocity vector, where c is a positive number. And it could be anything, so it could be 1/100th, it could be 1,000. The easiest one is 1, you know. So an acceleration vector of 30, 30, negative 10 meters per second squared works. Or if c is equal to 2, 60, negative 20 meters per second squared works. It just needs to be a vector that's a positive number times 30, negative 10. 3, negative 1 would work. Anybody have any questions about the reasoning on that? Okay, so now for part B, how do you get it to slow down? Yep, yeah. So, okay, so remember what happens when you multiply a vector by a positive number, it stays in the same direction. If you multiply it by a negative number, it switches to the opposite direction. And so what we're talking about here is we have a velocity vector in this direction. Well, that's not true. Let me draw it the way it really is. So something like that. Okay, that's the velocity vector. To make it speed up, we need something in that same direction for an acceleration. To make it slow down, we need it to be in the opposite direction. So for part A, you multiply by a positive number. So it's always going to be a positive x and a negative y. For part B, to make it go in the opposite direction, you can multiply it by any negative number. So C being equal to -1 doesn't work for part A, but it would work for part B. Yeah, yeah, right. So then, um, so for part A, you have a vector like this for the velocity. Um, we want a parallel part of the acceleration that's in the same direction. And then you could have a perpendicular part that was like this if it's turning. But this one says it's not turning. And then your total acceleration would be, depending on how big these vectors are. Yes, if this component was really big, it could have a negative x component. Yeah. But it wouldn't keep going in the same direction without turning. That perpendicular part would make it turn. Okay, so for part B, the acceleration has to be equal to, I'll say the constant is lowercase k. So k times 30 negative 10, where k is negative. And that could be any negative number, negative 1/1000th, negative 1,000, anything. And so the things that would work here would be like -3, +1, or -30, +10. Anything like that would make the object slow down. Because that entire acceleration is parallel to the velocity. So like think about how we talk about it in lab, like the parallel and perpendicular part. The parallel part is the one that determines whether it speeds up or slows down. And then the perpendicular part is what determines whether it's turning, which way it turns. So if your entire acceleration is parallel to the velocity, it's speeding up or slowing down and no turning. Well, so slowing down, but that would be a little trickier for me to ask. I wouldn't ask that because the math is a little trickier. I mean, because you'd have to figure out a vector that was perpendicular to that one, and the math is trickier on that. But figuring out a vector that's in the same direction or a vector in the opposite direction, that's not that tricky. You just have to remember that you're multiplying by either a positive number or a negative number. Any other questions about those two? Yep. Yeah, that works. Well, remember that, so this one is a velocity. Okay, that's a velocity. And we're trying to come up with an acceleration vector. So they're not really like the same thing. Um, if the acceleration was equal to zero, though, the velocity would stay the same. Okay. If, yeah. And then any acceleration that's in the same direction as velocity would make it speed up. Remember, constant velocity is the same as zero acceleration. So yeah, it's a lot of stuff to juggle around, I know. But, okay, so now for part C, say that's the acceleration vector, and see if you can calculate the object's displacement if it undergoes that acceleration for 10 seconds. That's easy. Okay, so for this one, so when we do these problems, at least when we do like the free fall ones, we always start by defining our time equals zero and our time final and stuff. Um, well, this one, we are going to have to choose like the time equals zero and the time final instant. But if you're given acceleration or velocity or position vectors as components, components can't be defined until the coordinate system is chosen. So that's already been chosen for you. We don't even have any connection to like the real world with this problem, so we don't have any way to say like, let's put the origin of the coordinate system on the ground and you know what I mean? So for our time equals zero, um, we're going to choose that initial velocity. Uh, so that's the given initial instant. And then our time final is just going to be 10 seconds. Our origin and the coordinate system are both just given. But now we can think about what we know and what we want. Our time final is 10. Our acceleration is the vector negative 25, was it? So AX is negative 20, AY is positive 5. Our initial position, um, you know what? What I said here isn't quite true. Sorry about that. So the coordinate system direction has already been chosen, but the origin hasn't been chosen. So let's choose the origin to be at the object's position at time equals zero. This is already chosen, given. Okay, so then at the initial position, if the origin is at the object's position at time equals zero, that's another way of just saying that the initial position is going to be 0, 0. So PIX is 0, PIY is 0. And we want to find PFX and PFY. We can do it in any order. We know the initial velocity, VIX, is 30, and VIY is negative 10. And we don't know the final velocity. Okay, so is there an equation that we can use for either one of these? If we want to find pfx first, I think it'll work to calculate pfx is equal to pix plus bix tf plus 1/2 ax tf squared. So pfx is equal to 0 plus 30 times 10 plus 1/2 times -20 times 10 squared. And so that's 300 minus 1,000. And so that's -700. And the units for the final position are meters. And then we can use the y version of that equation to calculate PFY. That's equal to PIY plus BIY TF plus 1/2 AY TF squared. So PFY is equal to 0 plus -10 times 10 plus 1/2 times, what was the acceleration? +5 times 10 squared. So PFY is -100 plus 250. So +150 meters. And then if you put those two together, you get that the final position vector is -700 x +150 y. And then it asks for the displacement vector. So to get the displacement vector, you go the later position minus the earlier position. So that's equal to -700 +150 minus the starting position. We chose the origin to be at that starting position, so this is just 0. And so that final position was equal to the displacement vector. Yes? Only if the velocity is constant. So in this case, the velocity has a lot of different directions, because let's draw out these vectors, okay? So we're starting out with a velocity vector of 30, -10. So we're starting out with this velocity vector. Okay. The acceleration vector is -20, +5. So -20, +5. So something like, let's see, something like this. Okay. And so this acceleration vector is not entirely parallel to the velocity, and it's not entirely perpendicular to the velocity. That means, so there's a parallel part and a perpendicular part. It's not just one or the other. And since there's a perpendicular part, it's going to be turning as it goes. Okay, so little by little, the direction is going to be changing. And that's why the displacement vector. So if that acceleration vector did happen to be exactly parallel to the velocity, like in this case, if it was tilted up a little bit and was exactly opposite the velocity vector, then this would start slowing down because the parallel part is opposite the velocity until it stopped. Then it would start speeding up in the opposite direction. And then when you took the displacement would be in the same line as the velocity. Mm-hmm. Are you talking about like number one? Well, so if you choose your origin location to be where the object is at time equals 0, then your initial position will be 0, 0, and then you can just calculate the displacement. Yep. Okay. Let's do another one. Okay, so let's say there's this on the ground, there's this contraption that's holding up like a Nerf gun. And let's say that this Nerf bullet is going to be shot from a height of 1 meter. And it's going to be shot at an angle of, let's say that's 30 degrees above the horizontal. And let's say we want this Nerf bullet to land on the ground let's see. So we want it to land on the ground at a specific location. Okay, so how far away do we have to put the gun to make it land at this location? I need to say that the bullet is going to be shot at, let's say, 20 meters per second. Okay, so work through that one, and then I'm going to do a follow-up to this one after we're done. All right, so put the origin, I mean, you can put it where you want. I'm going to put it on the ground underneath where it's shot from. The time equals 0 is going to be the instant that it's shot. Time final is when it hits the ground. And the origin and the coordinate system are shown in the picture. We don't know time final. We're okay without it if we don't need it. Acceleration, it's free fall, so AX is 0, AY is negative 9.81. Initial position, PIX is 0, PIY is 1. Initial velocity, so that comes from, if this is the coordinate system, the vector has a magnitude of 20 and an angle of 30 degrees above the horizontal. So the initial velocity vector is 20 times cosine of 30, 20 times the sine of 30, and that is 17.32 for x and 10 for y. I left out the final positions. That's what we're trying to find. So we're trying to find PFX, and we don't know the final velocity, so I'll leave those out. We do know one deep down, but we never write it on here. What's the one part of the final velocity that we do actually know? PFX is the one that we know because gravity only accelerates things in the y direction, up and down, down. And so the horizontal components are totally unaffected by gravity. So VFX is still going to be 17.32. And that's always going to be the case in free fall problems if your y-axis is up. Okay, so is there an equation that works with this? No. So what's our plan B? Yeah, so we want to find time final. So to find time final, we can use PFY is equal to PIY plus VIY PF plus 1/2 AY PF squared. PF, and we know PFY is 0 when it hits the ground. So 0 is equal to 1 plus 10 PF plus 1/2 of negative 9.81 times TF squared. How do we solve this? Yeah, quadratic. And what answers do you get for this? Anyone do that? 2.13? Is that what you said? Okay. And then what was the second one? Negative something. Negative 0.095. Okay, so we don't want this one, so we want this one. And now we can go back and calculate PFX. So PFX is equal to PIX plus VIX PF plus 1/2 AX PF squared. So So PFX is equal to 0 plus 17.32 times 2.13 plus AX is equal to 0, so that term goes away. And what do you get for PFX? 36? That's a lot. 36.85 meters. It's like over 100 feet. Any questions about that? Yes. Because the target's on the ground. So we don't know how far away it's going to land, but we do know it's going to be at the same height as our origin because we put our origin at the ground. Yeah. Mm-hmm. You wouldn't. So if the target was 1 meter up in the air, yes, that's right. And actually, I want to do one more problem, and I want to do that with a height of 1.5 meters. And something is going to happen that makes this a little more complicated, even though everything else is the same. Um, so now, same question. But this time, the target is at the height 1.5 meters. Okay, so the way you solve this problem is basically identical, but something confusing happens. Something weird happens. What's going on? We'll get the answer too. Okay, so see if you can work through that one. No, go ahead. We're not really doing it. Okay, so I'm going to use the same time equals 0, time final, all that stuff. So what we know and what we want. So we don't know time final. We know the acceleration. The initial position is 0x, 1y. The final position, we know that pfy is 1.5. We're trying to find pfx. Yeah, that's just the loop of my 9. The initial velocity, VIX, is 17.32. VIY is 10. And we're going to act like we don't know the final velocity. Okay, so there's no equation that lets us solve for PFX. So we try to, bless you. So we try to find TF first. So to find TF, PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. Okay, and so this says 1.5 is equal to 1 plus 10 TF minus 4.905 TF squared. And arrange this like a quadratic equation, and you get negative 0.5 plus 10 TF minus 4.905 TF squared. And what happens when you use the quadratic formula for this? Two positive numbers. Yeah, right. And what are they? 0.5, what? 0.003. Okay, so what's the deal with this? Like, what's going on in this case? So now it's harder to choose, right? And so physically, in a problem like this, you have to make sense out of what those two answers are so you can figure out which one you want. It turns out in this case, each one means something. Like, really, you could choose either one if all you care about is hitting the target. But here's what's going on. So the the bullet is going to follow a parabolic path like that. And in that parabolic path, it's going to get to a height of 1.5 meters two different times. It's going to get to this one at a time of 0.503 seconds. And it's going to get to this one at a time of 19.49. And so choosing these times is choosing whether you want the bullet to be on its way up when it hits or on its way down when it hits. Okay, so sometimes in free fall problems that'll happen. You'll solve for the times, and both answers will be positive. And so you can't immediately just reject one and take the other one. That happens. Just remember that this is a parabolic path. That the um, and that object is hitting your desired height two different times, and then based on that, you have to decide which one of those two you want. Okay, so um, mhm, yep. Um, the target is a height of 1.5 meters, but we're still starting at a height of 1 meter. So the thing that's different in this is that the target is above the starting point, and any height that you choose, unless you happen to choose the exact highest point, because there's only one time that it reaches the highest point. Any other height above where it's shot from is going to have two answers. Any other questions? Well, let's just finish. So PFX is equal to 0 plus 17.32. Let's say we're going to hit it on the way up, 0.503 plus AX is 0, so that goes away. PFX. And so the answer is about 8.66. Yeah, 8.66 meters. Right? Yes. So I guess it depends which way the target's oriented now that you say it like that. If the target's oriented like this, it doesn't matter. If it's oriented like this, then yeah, we'd have to use the later one. Hmm. So the way I was picturing it is we're just trying to figure out how far away horizontally we have to put this gun to make the bullet hit that target. And since it'll hit either one of those points, it doesn't really matter. If you were really using this calculation um, to try to make it hit the target, there is one reason why you'd want to choose the closer one, and that's that uh, not as much air resistance is acted to mess up your results. You know, air resistance is acting a lot longer here, so it's going to fall short of that target because of air resistance. This one would be a pretty good calculation. Mhm. Yeah, or you could just pick either one. But this isn't really as much like a thing that's going to come up on tests. It's more of a thing, just sort of like, I don't know. Sometimes there's a little interpretation you need to do. Um, any other questions? Okay, let's stop and the people who have lab tonight, let's start lab at 10 after 7. Start early and get out of here early.